Oh, I guess I'm up and running here. Didn't see it. All right, let's get that going. All right. Um, Center the camera. Okay. All right. So gonna try to talk through some, I think, important concepts with respect to topics that you can learn at the elementary school level, topics that are important at the early algebra level and beyond. All right, so let's start with things we know. That volume is length times width times height. And I am going to create some cubes, some boxes, little tiny boxes. And we're going to use user-friendly numbers, and we're going to do a little exploring. All right, it's kind of dark. I hope this is going to come out okay. And early on in elementary school, I think you probably learned how to multiply by negative numbers. -3 times -3 times -3 is -27. Whereas +3 times +3 times +3 is 27. And we get some perfect cubes, some nice user-friendly numbers. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 2 times 2 times 2 is 8. And that gives us 5. Right. And then I think in the 1600s, I think René Descartes, I have to go check my times and make sure I have my dates correctly. But there, somewhere around early 1600s, René Descartes gave us this coordinate system, input-output coordinate system. And they're just two rulers, one horizontal, one vertical, that give us measurements. And so I can plot these values. I can show where 0, 0 is on his little mechanism here, and I can show where 1, 1 is, over 1 up 1, over 2 up 8, over 3 up 27. And I can plot places like this is 3 by 3 by 3 gives us 27 units of volume. 2 by 2 by 2 gets us 8 units of volume, so on and so forth. And I already see a mistake I have here. Okay, tried to put a lot of this stuff down already. So if we look at change, and change can often be written as a symbol in that triangle. If we look at the change from one situation to the next, I can see that if my side of my cube changes by 1, from 0 to 1, my volume goes from 0 to 1 as well, and that's a 1-to-1 change. If my side of my cube goes from 1 to 2, I'm still changing by 1, 2 to 3 still changing, side length by 1, but my volumes change differently. I go from 1 unit of volume to 8, that's an average rate of change, average rate. And I can show that with just connecting a line segment from one location to the next. And I can see that my volume has changed from when it was 1 unit cubed is 1, to 2 units cubed 8, a 7-to-1 average rate of change. And I think that I can show that average rate of change, a 1v1, 7-to-1, a 19-to-1 as little line segments. And I probably could have done the same thing in the negative direction. And if I did, I'd get something that looks like this, which gives us a feel for the continuity of the cubic. There's also something very interesting here. I can see that, negative volume, it's hard to talk about negative volume, but let's talk about just going from -27 to -8. Well, on a number line, here's -27, here's -8. I'm going up, I'm increasing, right? A smaller negative volume, it's awkward, the language of magnitude, is a bigger number than its previous one. Right? So I'm always increasing. This function is all, we read graphs from left to right, this function is always increasing, but it's increasing at a minimum rate right here, right at 0. The question is why? Well, let's dive into it a little more carefully. There goes my cart. Over here. Yep. New whiteboard. Well, let's look at going from 0 to 0.001. Let's make it a smaller size increment. dimensions of our box, of our perfect box. If I cube 0.001, I get 0.000000001. And if I cube 1, I get 1. But if I cube 1.001, I get 1.003.003.001. And if I cube 2, I get 8. And if I cube 2.001, I get 0.012.006.001. 3 gets me 0.027.027.001. There's some patterns here. Question is why? Why are we getting patterns? Well, the geometry of this isn't going to change. Cubes are like times width times height. Perfect cubes are x times x times x. And I can tell you what something cubed is, then I should be able to tell you how it's changing at that instant. And it turns out it's a minimum. So we were always increasing. And if you want to pause the video now, I know when I first started looking at this from a geometric standpoint, I had to pause and say, what's going on? And so later on, we'll tell you what a 4v4v4, how that's changing. But maybe you can figure it out. If you want, pause the video, even think about it for a couple of days and then pick up the video again. Got to start these conversations. All right, so let's move to early algebra. Let's have a box whose volume's changing. And it's not a perfect cube anymore. We've got a length of x. We shorten it by 2 units. We shorten it by 10. And we get this kind of flat box. And let's just look at multiplication, just the process of multiplication. What's 2 times 3 times 6? Well, we rename 2 times 3 and we do 6 times 6. That's how we do it. So how would I do this multiplication? I'll rename the first 2 numbers. X times x, x squared, x times minus 2x. And then I'll multiply it times x minus 10. And if I do that, I like to make columns where like terms are in a column. And I'll be doing that again later in the video. And we get x cubed minus 12x squared plus 20x. So that's our volume. Our volume comes from this multiplication for this particular box. However, we also study when our products are equal to 0. Very helpful. And I can see when that's happening. That's happening if I let x equal 0, no volume, x equals 2, no volume, and x equals 10, no volume. However, if I put 11 in, I get some volume out. 11 times 9 times 1 is 99. So I'm way up here. I mean, we get something that looks like this. All right. And we study that in algebra. Rational roots theorems and things like that. All well and good. I don't think it's the most interesting stuff that we do. I think the most interesting stuff we do is to look at where might this cubic be? How might we write this cubic differently so we can see change from a given location? X cubed is really x minus 0 cubed plus 0 times x minus 0 plus 0. That's the graphing form for a cubic. We wouldn't write that way. We would just say y equals x cubed. But how are we going to get to the graphing form for a cubic? I've really jumped ahead quite a bit here. So let's keep moving down the wall. Starting some conversation. Let me make sure I've got the video centered nicely. All right, I do. So we've got our length, our width, our height. We're talking about dimensions, early dimensions. We're on the coordinate system. And it appears that there's a number here that's most important because I got a concave down shape and then a concave up. The shape changes. There seems to be some symmetry around this place. Then we might want to ask, well, what is that x value? And of course, because I'm making this video, I'm making the numbers as easy as I can. Well, it turns out that we can reshape. I got to get my cart now. I'll keep talking. We can reshape this cubic into what's called a perfect cube, whose analysis we already studied 5 minutes ago. All right. So we have x minus 2, and x minus 10. And they correspond to 0, 2, and 10. Gets rid of the volume of the box. I have a box over here. Let me get it. And if I want to get rid of the volume of this box, all I have to do is crush it, step on it, get rid of the height. No volume. Or I could squeeze it this way, get rid of the width. No volume. Or I could get rid of the length. No volume. All right. Keep my cap here. So we can see that it's easy to use this calculation for finding volume. For instance, if I let x equal 11, that's an input. It's a calculation. I get an output. And if I put 12 in, each number gets one bigger. And it looks like I get, what? 120 times 2, 240. That's significant change. Yeah, it seems like things are going up pretty quickly over here. Yeah, they definitely are. Now, what happens if I even off the sides of the boxes? We do that. That's what completing the square is for those folks who are in my class now that are working with that. We've been completing the square. It's a fancy term for put the quadratic in graphing form. And I've drawn those pictures for you. And I've drawn these pictures for you, but I think repetitive conversations are necessary to understand math. So we're repeating things. All right, so if I add these three numbers up and I divide by 3, I get the number 4. And coming back over here, yeah, kind of looks like x equals 4 is where this is happening. I don't think it's coincidence. So let's cube x minus 4. Let's see what we get. We cube x minus 4. Well, one thing, if I put 4 in, it acts like this function did a minute ago. All right. And if I put 0.001, I know my change is, oh God, can I even fit it on here? 3, 4, 6, 7, 8, 9. You know, the first 3 digits don't change at all. And if I make this 4.001 to answer an earlier question, which if you're still thinking about, pause the video because I'm going to give you the answer now. I get 4.00, I get this thing cubed, but I get I get the same thing. 0.000000001. No change there. What do I get if I cube x minus 4? I'll do it for you quickly here. X minus 4 squared. We've been working on binomial squaring. You should be able to see how I derived that. Times x minus 4. Well, this is where I do the columns. And if I do the columns, it looks like I get that. That's what I get if I multiply just x minus 4 cubed. I don't get this. I get something different. And yet, we know that at 4, remember at 4, got this graph, at 4, we're decreasing. So I need a linear component here to make that happen. Because I know that's flat. And I know at x, that's flat. Moving this thing up and down is not a problem. But I've got to get this thing to be mimicking that rate of change at a new location. I got to bring in a little linear function here. Right? And let's see, where did I go with that now? Well, I did a little work. Just this isn't the way I derived this originally, but I thought it might be easier to understand it this way. So I put a 5 in. 5 for x. And that means I'm doing 5 times 3 times -5, which is -75. Okay. But I also know that when I put a 5 into the x minus 4 cubed, x minus 4, right? When I put a 5 in here, I got to get the same answer out as if I put a 5 in the original. Now, the original was, oh God, I hope I don't have to do this video again. I'm losing my train of thought. All right, if I put 5 in there, I got 125. Did I do it somewhere so I can save time? Thought I did it somewhere. 125 minus 300 plus 100. So yeah, okay, so minus 75 is correct. Right, and yet to get minus 75 out, when I put 5 into this emerging graphing form, I get this calculation. I need minus 28. I need this to become minus 28 to get back to x cubed minus 12x squared plus 20x. So where did that all come from? How did I do that? Well, let's keep going here. I put some things on the board. Let's see if this is something I need to talk about as well. Let's move this down. If I had a better grasp of how to use technology, I probably could do this presentation a whole lot better, but I don't. Old guy here. All right, so I just proved that if we multiply this out, that's all I did here. I just proved that if I multiply out what I wrote over here, I would get the graphing form for a cubic. All right, at 4, you put 4 in, you get minus 48. You get that location, and minus 28 would be the rate at which I'm changing there, and that happens to be a minimum rate. I'm going down fastest right here. Right, I'm increasing, but less quickly until here it's 0. I'm flat right there. I'm not going up or going down, and I'm going down like a roller coaster. Boom, I hit that spot where I'm going the fastest, and then the track starts to come back up again, and there's where your stomach starts falling out of your body. Now, whether you realize it or not, we've been working with some limits. We've been looking at erasing error. So for instance, I did 2 cubed is 8, 2.001 gave us that a little while ago, but I could have made that change in dimension smaller. I could have added decimal places. And if I did, you can pause the video. I didn't take a calculator. I hope I'm remembering correctly. I hope it's 3 times that x value for that pattern. Not, I'm going to have to go back to the drawing board. But I'm sure this one, all right, and what do I have for change? 1, 2, 3, 4, 5 decimal places. 1, 2, 3, 4, 5, 12 to 1. What do I have here? 3 decimal places, 3 decimal places. 1, 2, 3, 12 to 1. And this one's more accurate. Keep pushing those decimal places out. I think at 8, we're going up to 12 to 1. Go back to our up 1 to 1, up 7 to 1, up 19 to 1, right? And what I'm suggesting is right there, I'm going up to 12 to 1. It's certainly in the middle of that pattern. So now what do you start learning at calculus? Well, you start working with rates of change, right? From a geometric standpoint, let me get my box. So here's a box. And maybe you figured out the rate of change for a cubic already. It's right here. So that has volume. This box has volume, and I am going to make the volume go up a little bit by putting a little sleeve on it. Right? So let's say that this is a solid. Well, that solid just got bigger. By how much? Well, we got to look at the dimensions. Well, first off, you're looking at, I think, a square with a little bit of thickness. With a little bit of thickness right here. All right, what's that dimension with respect to the change here? I think that's the 0.001. That's the height of this little part of the sleeve, which is a square. Oh yes, a square. And maybe it's a 2 by 2 square. And 2 times 2 is 4 times 0.001 is 0.004. And if I do that 3 times, you do the arithmetic here. You tell me what you get. 0.004 new volume, 0.004 new volume, 0.004 new volume. I do believe we have three of these things. What did we say? One was at changing it 1 to 1.001. We've changed to 1.003, 003, 001. Huh. X squared, 1 times 1, 1 times 3. X squared, 2 times 2, 4 times 3. 3 squared, 9 times 3. There were your first three values of the cubic change at 3. Now you're doing calculus. So, how does x cubed change 3x squared? That's how it changes. It's a formula. How does x squared change? Well, that's actually a different formula. And to increase the area of a square, I got to draw a sleeve, 2 side lengths. So x squared is 2x times minus 12 minus 24x. You bring in a multiplier, like if you earn $5 an hour and I tell you I'm doubling your wage, you know your rate of change real quick. Okay, so I'm just taking 2x and multiplying it by this. And how does the linear function change? It's always going up 20 to 1. You don't care from what x value to the next x value, you're a ratio of 20 to 1. It's constant change. And how does a constant change? It doesn't. Constants don't change. If you see that number change, you call me. All right, write me a comment and I'll get you some help. Okay, we'll talk and in a nice way too. Very kind, empathetic way. I've had a lot of trouble with numbers over my life, and if you're seeing that number change, we need to talk. All right. So if I talk about rate of change, well, I think I'm talking about acceleration. So let's talk about the rate of change. So x squared is 2x times 3, 6x minus 24. Oh, 0. Oh, that seems to be where the acceleration changes from deceleration to acceleration. Maybe concave down to concave up. Maybe concave down to concave up happens at 4. We have 6x minus 24 is a linear function that goes from negative to positive, from concave down to concave up. Yeah. And if I put 4 back into the function, into the rate of change function, lo and behold, I get minus 28. 4 squared times 3, 4 times negative 24 plus 20. I get negative 28. Oh my goodness. So that means I have a tangent to this. I have a tangent right here. And that tangent line is minus 28, x minus 40. And I also have a function that's not changing at 4 comma minus 48. That's flat, and that comes from this, which means that this could have been written as x minus 4 cubed minus 28, x minus 4 minus 48, and we get a whole lot of information from writing it that way. We get what's called the point of inflection. We get the rate of change at the point of inflection. I think that's more important than the roots, understanding this geometry. All right, and so how do we get x equals 4? How do we get that? Well, that's what minus b over 3a is all about. That's what minus b over 3 of a is all about, right? The average of the roots, minus b over 2a, the average of the roots of a quadratic, minus b over a, the x-intercept of a linear function. You know, in the ax plus b format, minus b over a is where a function goes from negative to positive or positive to negative. Minus b over 2a is where a quadratic either hits a max or hits a min. Minus b over 3a finds where a cubic changes concavity, points of inflection. Whoa. Not sure what I just did there. And it turns out that when you set these to 0, these quadratics to 0, we're looking for rates of change that are 0. Well, I hope you can see that's right here and right here. That's where the function's flat. And I run out of white space. I can't keep this lecture going. So I can't talk a little bit about how you find the x values, but they're right here. And it's all about the interplay of these slopes. when this is pulling down at the same rate that the linear component is pulling up, and I could have said that improperly, but when their rates are opposites, right? If I'm pulling at a certain rate and increasing my pull, but when I start out, I'm just old. And I'm already old, I'm not starting out. Anyway, if I have an increasing rate, I start with a slow rate and faster rate in this direction. What if somebody's pulling in the other direction at a certain constant rate? Well, at some point they offset each other. And that's what is happening with these maxes, local maxes and local mins. And it turns out it comes from this formula. What's H? The horizontal shift minus B over 3A. And how do I get the slope at that instant? C minus 3AH squared. I don't have time to do that now. I've run out of board space, but it goes back to algebra 1. I don't get what I want. I got a marker. I write in what I need. All right, maybe I can do an addendum to this lecture because this one, I don't know, it feels like I've been at this for half an hour easily. All right, but it's important concepts. Otherwise, you're just memorizing formulas, which, you know, can work. Some people have a gift at mathematics and can just work with it in many ways that I can't. That's for darn sure. But I like to see where things come from. I mean, I figure this is my job. I've been teaching high school math, and I'm not going to look at much beyond. Although I think it's important that I taught AB Calc, that I look at Taylor polynomials on a little bit, sequences and series. But what I teach, I try to dive in deeply. And this is what I'm seeing. And I think it's important that you try to think about these things. So there goes that. And I'll post this, and maybe some folks will look at it. It takes some, what's going on here moments. But once you figure that stuff out, it makes more sense. I think that's what we should be about. Okay. Ciao.